I need to lay this out for you with precision because this isn't an issue of mere technology. It's not a situation where we just need more powerful rockets or a more efficient propellant. The challenge is far more deeply ingrained than that. The obstacle is woven right into the fabric of physical law itself, and I'm about to demonstrate exactly why. Let's begin with a basic concept. How distant are the stars? This is something people don't truly grasp. They look at the night sky and think, yes, those are very far, but they lack a genuine comprehension of what far signifies in this context. The star nearest to us, aside from our own sun, is named Proxima Centauri. It's situated approximately 4¼ light years from here. Now, what does that measurement represent? A light year is the span that light covers in a single year, and light is swift, inconceivably swift. Light moves at a rate of 186,000 miles in a single second. Every single second. In just 1 second, a beam of light could circumnavigate the globe 7½ times. So, over the course of a year, light covers a distance of about 6 trillion miles. 6 trillion miles! And Proxima Centauri is 4 times that distance from us. To give you a proper sense of the scale, our most rapid space probes, the ones we have actually constructed and dispatched into the cosmos, achieve top speeds of perhaps 40,000 miles per hour. That sounds quick, doesn't it? Yet at that velocity, a journey to Proxima Centauri would require about 75,000 years. 75,000 years. That period is longer than all of documented human history. It's a greater span of time than civilization has even been around. So it's obvious that if we have any hope of reaching another star within a plausible time frame, like a single human lifespan, we must travel vastly, vastly faster. We would need to achieve some considerable percentage of the speed of light. Let's imagine we want to reach Proxima Centauri in 4 decades. That would necessitate traveling at about 10% of light speed. This is the point where the true difficulties begin, and they originate from 2 distinct sources. The first hurdle is what is known as the rocket equation. The second is a consequence of Einstein's special theory of relativity. Allow me to elaborate on both. The rocket equation was conceived by a Russian scholar named Tsiolkovsky way back in the 1890s. It is an elegant formula, quite straightforward, but its implications are severe. Here is what it dictates. To make a rocket accelerate, you must expel something from its rear. This is a fundamental application of Newton's third law. For every action, there is an equal and opposite reaction. You eject exhaust backward, and the rocket is propelled forward. But herein lies the dilemma. The propellant that you intend to burn at a later stage of the journey must be carried with you from the start. Therefore, to achieve higher speeds, you require more fuel, but that fuel adds mass. This makes your rocket heavier, so you need even more fuel to accelerate that additional fuel. And that new fuel also has mass, so you need more fuel to accelerate that fuel. Do you see the predicament? The growth is exponential. The equation is expressed as follows. The achievable change in velocity is the product of your rocket's exhaust velocity and the natural logarithm of its mass ratio. The mass ratio is the weight of your rocket when fully fueled divided by its weight when empty. Now, let me provide some numbers to illustrate how dire this situation becomes. Suppose you possess the most advanced chemical rocket imaginable. Its exhaust exits at roughly 4,500 meters per second. That is quite impressive. It's the standard for our top chemical rockets. Now, to enter Earth's orbit, you require a velocity change of about 9,700 meters per second. If you work through the rocket equation, you discover that approximately 88% of your rocket's total mass must be dedicated to fuel. A mere 12% is left for the rocket structure and its payload, the very thing you are trying to deliver, and that is just to get into orbit. So what happens if your destination is another star? To travel at 10% of light speed, you need a velocity change of 30 million meters per second. 30 million using chemical rockets. Even if you could miraculously design a rocket structure that had zero mass, a pure vessel of fuel with a payload on top, you would still be unable to achieve it. The rocket equation demonstrates that it is a physical impossibility. The required mass ratio would be so astronomical as to be nonsensical. You would need billions upon billions of kilograms of fuel for each kilogram of payload. All right, so you might say, let's abandon chemical rockets. What about nuclear propulsion or fusion rockets, where you fuse hydrogen atoms together, mimicking the sun? Well, that is an improvement. fusion rockets could have exhaust velocities, perhaps 20 or 30 times greater than their chemical counterparts. But even with fusion, once you perform the calculations, you are still faced with enormous mass ratios. For a round-trip voyage to a nearby star at 10% of light speed, even with flawless fusion technology, you would need on the order of 1,000,000 kilograms of fuel for every single kilogram of payload, a ratio of 1,000,000 to 1. And bear in mind, we have yet to master controlled fusion for power generation here on our own planet, let alone inside a rocket hurtling through space. We have been working on it for 70 years, and the effort continues. So then people propose, what about matter-antimatter annihilation? When matter and antimatter meet, they convert their entire mass into energy. This represents the most efficient energy source conceivable under the laws of physics. It's Einstein's E equals mc squared, correct? The entirety of the mass transforms into energy. Yet even with matter-antimatter engines, even with this perfect power source, you are still confronted with challenges. For a round trip at 10% of light speed, you would need about 1,000 kilograms of fuel for every kilogram of payload. That's a significant improvement. But here is the catch. We are barely capable of producing antimatter at all. The total quantity of antimatter ever created by humanity, if you gathered it all together, would not be sufficient to heat a cup of tea. Creating antimatter demands immense expenditures of energy, and containing it so that it doesn't touch regular matter and obliterate itself is exceptionally challenging. We have no plausible way to scale this up. And all of this, everything I have just described, pertains only to the fuel problem. This is solely the consequence of the rocket equation. We have not yet even begun to discuss Einstein. Einstein's special theory of relativity reveals something both extraordinary and vexing. No object with mass can ever attain the speed of light. Not that it is merely challenging, but that it is genuinely impossible, forbidden by the very laws of the universe. Here is the reason. You are familiar with Einstein's renowned equation, E equals mc squared, energy equals mass times the speed of light squared. But that is, in fact, a simplified version of a more comprehensive equation. The complete formula incorporates your kinetic energy, the energy of your movement. As you travel faster and faster, your kinetic energy increases. But as you get closer to the speed of light, a peculiar phenomenon occurs. The energy no longer grows in simple proportion to your speed. It approaches infinity. As you inch ever closer to the speed of light, the energy required to accelerate even slightly more climbs toward an infinite value. Consider the implication of this. To reach the speed of light, you would need an infinite amount of energy. Not just a vast quantity of energy, not just more energy than we currently possess. Infinite energy. It is undoable. It is not a question of constructing a large enough power source. The cosmos itself prohibits it. And there's another way to conceptualize this. In relativity, as your velocity increases, a factor we denote as gamma emerges in all the relevant formulas. When you are moving at low speeds, gamma is very close to 1. But as your speed approaches that of light, gamma grows larger and larger, and it becomes infinite right at the speed of light. This gamma factor influences everything. It affects your energy. It affects the passage of time for you. If you were somehow able to reach 99% of the speed of light, gamma would be approximately 7. This means you would require 7 times more energy than classical physics would predict. At 99% of the speed of light, gamma is about 22. At 99%, gamma is about 71. Do you see the trend? The nearer you get to the speed of light, the more impossible it becomes to go any faster. So, even if you were able to resolve the fuel dilemma, even if you possessed an unlimited supply of antimatter or some other fantastical energy source, you would still collide with this insurmountable wall. The speed of light is an inviolable barrier for anything that has mass. Now you might be thinking, what about those ingenious concepts from science fiction? What about warp drives or wormholes? Very well, let's explore those. The concept of a warp drive is derived from general relativity, Einstein's theory of gravity. The principle is that instead of propelling yourself through space, you distort space itself around your vessel. You generate a bubble wherein space is compressed in front of you and expanded behind you, and this bubble then transports you. Within the bubble, you are not exceeding the speed of light relative to your immediate surroundings, so you avoid violating special relativity. This is predicated on a solution to Einstein's equations developed by a physicist named Alcubierre, and from a mathematical standpoint, Yes, these equations can be written down, and they are consistent. But here is the catch. To make this work, you require something termed exotic matter, which possesses a negative energy density. Now, what does that signify? In our everyday world, energy is invariably positive. Matter has positive energy. Even the vacuum of space, as quantum mechanics shows, has a positive energy density. But for a warp drive to function, you need negative energy, and a great deal of it. Not just a minute amount, but the mass energy equivalent of a planet or even a star. We have never observed exotic matter. We do not know if it can exist. Certain quantum phenomena might create infinitesimal amounts of negative energy under very specific conditions, but scaling that up to what would be necessary for a warp drive, we have no clue how to do it. It may be fundamentally impossible, and wormholes suffer from the same issue. A wormhole is like a conduit through space-time that connects two remote locations. If you could construct one, you could enter it and emerge light years away almost instantaneously. But to keep a wormhole propped open, to prevent it from collapsing, you would need the same type of exotic matter with negative energy and in enormous quantities. Furthermore, even if you could fashion a wormhole, there is another complication. To establish a wormhole that allows travel between 2 points, you must first transport the 2 mouths of the wormhole to those locations. And you cannot dispatch one mouth of the wormhole faster than light to position it. Therefore, to create a wormhole to Proxima Centauri, you would first have to slowly transport one end there at sublight speeds, which brings you right back to the original challenge. So, what is the upshot of all this? Well, it indicates that interstellar travel is not merely arduous, it is pushing right up against the boundaries of what physics permits and possibly extends beyond them. Could a highly advanced civilization accomplish it? Perhaps. But it would demand either technologies so far beyond our own that they are inconceivable to us, or a new understanding of physics that we have yet to attain, and one cannot simply presume that new physics will come to the rescue. The physics we currently have been tested with extraordinary success. Every prediction of special relativity has been validated in innumerable experiments. These effects are not theoretical. Particle accelerators routinely accelerate particles to 99 to 99% of the speed of light, and they observe these phenomena precisely. The particles become progressively more difficult to accelerate as they approach light speed, exactly as Einstein foresaw. Now there are some clever concepts that might render interstellar travel just barely feasible. Light sails, for instance, where you propel a very lightweight craft using lasers or sunlight. You don't need to carry fuel because the light provides the propulsive force, but you still need to source the energy to power those lasers. And decelerating upon arrival at your destination is another immense challenge. Or there are generation ships where you don't even attempt to travel quickly. You simply construct a massive vessel capable of sustaining a population for thousands of years, and your distant descendants are the ones who arrive. But the engineering difficulties of maintaining such a ship's functionality for millennia are mind-boggling. Or perhaps we don't send humans at all. Perhaps we dispatch minuscule probes, just a few grams of mass, that can be accelerated to high velocities by powerful lasers. The Breakthrough Starshot Initiative is, in fact, attempting something along these lines. But even that is incredibly difficult, and you are only sending cameras, not people. The essential point is that the universe is large on a scale that defies imagination, and the laws of physics make traversing those distances exceedingly hard. It is not analogous to building a better airplane or a more efficient rocket to the moon. It is contending with the fundamental limits of nature itself. Does this mean it is utterly impossible? No, I would not go that far. Science has surprised us in the past. It's possible there is something we don't yet understand about physics. Maybe there is a loophole we haven't discovered, but it would have to be something truly revolutionary, something that would overturn or expand our current knowledge in a profound way. And we must be realistic about this. We cannot just gesticulate and say, oh, one day we'll solve it. Perhaps we will. Perhaps we won't. The universe is under no obligation to provide us with easy interstellar travel simply because we desire it. The astonishing thing is that we can comprehend these limitations. We can calculate precisely why it is so difficult. We can see how the rocket equation and relativity collude to make the problem nearly insurmountable. That is the power of physics. We understand the rules of the game, even when those rules tell us that some of the things we wish to do are nearly impossible. And you know what? There is a certain beauty in that. The universe is vast and enigmatic, and there are boundaries to what we can achieve, but we can understand those boundaries. We can see with clarity why they exist. And who can say, perhaps someday someone will discover an ingenious way to circumvent them, but it will not be simple. It will not be a mere matter of superior engineering. It will demand either incredible technological leaps or genuinely new physics. That is what makes it so thrilling, and at the same time, so frustrating. We can see the stars, we can study them, we can detect planets orbiting them. But to reach them, that is a challenge of an entirely different magnitude. The physics is unambiguous. The stars are very, very far away, and getting there is not just hard, it is on the very precipice of impossible.